Dr. Inamori, distinguished guests, ladies and gentlemen, and also distinguished students in the upper balcony, I welcome you and I hope that I can inspire you. It is a great honor and a real pleasure for me to receive the Kyoto Prize. For my work in materials, to be in the footsteps of all the previous prize winners is a humbling experience. My field, metallurgy, later ceramics and material science, provided me with interesting and important problems that kept me happy and gave me the feeling of accomplishment during a long period of my career. How did this happen? How did I find these fields? What are the events that led to this day? In looking over my life in preparation for this talk, I've keep discovering small events that I'd forgotten about that later on turned out to be very important. And these were serendipitous occasions. These were things where I hadn't planned on something and it happened and it helped me. Now, let me tell you a little bit about materials or metallurgy as it was 60 years ago. There was very little science. There had been 3,000 years, and for some areas 6,000 years, of a remarkable craft experience. And people were always very smart, and whenever people have examined phenomena, do things, work, they discover rules, and these rules become codified. They get passed from master to apprentice, and they become the rules of the field. And so there was thousands of years of such experiences. And the amazing thing was that the craftsmen knew a great deal more about materials than the academics. The academics were philosophers. They followed rules that did not much depend on experience, on experimental experience. So let me tell you a little bit about this talk. I will do something personal. This is how I proceeded to go through my early years, through my schooling, and then my work at various institutions. I've worked for government, I've worked for industry, and I worked for academia. And then I'll talk about the phenomena that I've been associated with. So I'm going to talk a little bit about some craft paradigms and then some academic paradigms. Very good craft paradigm was the separation of silver from copper by using liquid lead to dissolve the silver from the copper. Now, this was an ancient craft. It was used in Athens 2,500 years ago, and the silver that was recovered this way was part of the wealth of Athens. And I was very pleased to discover that it had come to Japan and pretty much unchanged. And then I'll talk a little bit about steel, the Western tradition of steel, which was very different from the Japanese tradition of steel. And then I'll talk about academia and the misinterpretations that academics put on the field that kept the field from developing. So here is a wonderful Japanese print, and it is called here, you can read it, this is Namban Buri, the Buki, Namban Buki, the Southern Barbarian smelting method. I don't know how it became Southern, but because it came from Athens and it took over 2,000 years to come here. Lead, copper and silver occur together in the same ore, and if you just smelt the copper, you create an alloy of silver and copper, which is just like copper. But if you separate out the silver, you create wealth. So the first step was to mix the metal with lead, and the liquid lead dissolved the tin out, and this is the first step. And then you separate the lead with high bukijin, which is over here, which is the ash smelting silver. In fact, in the Athenian method, the lead was oxidized, so it became an oxide, and the silver was left behind. So here is a worldwide paradigm of how to do things. Now, let me go back. Steel, on the other hand, was very different. Steel was considered so much more noble than iron that it was considered a separate substance. In most languages, steel and iron have quite different names. It's Eisen und Stahl, it's fer and whatever it is in French, acier. And the way it was made in the West was by heating iron for several days in a charcoal fire. And the idea was that the fire would purify the iron. And this was a laborious process. Steel was not very common. It was a lot of extra work. And then in 1780, an alchemist working on something quite different, namely how acids dissolve metals, discovered that when he dissolved steel, there was something left over, and it was carbon. And if he dissolved iron, it completely dissolved. So all of a sudden, instead of steel being a highly purified iron, it became an alloy, a mixture of iron and carbon. And by weight, it's less than 1%. But it made this enormous difference in the material. And as soon as people realized that that's how you made steel, they could control it better, they made better steel, they made it much more quickly. And in fact, they used the Chinese method where they added high carbon cast iron to steel. So here was an example of a revolution from a very simple experiment and a complete paradigm change in the sense that now we knew steel was pure. Now, the academics were puzzled by this because they felt that solid, there should be no diffusion in a solid. How did the carbon get in? How did the evil things that were in the iron beforehand that were removed by the fire come out? they felt evidently that anything that was solid, the atoms wouldn't move, the atoms would be stationary, and they also felt, and this is still true from the time that I was a student, that solids are chemically inert. They don't react. There is no chemistry. The molecules in a solid are solid. And they obey the law of definite proportion. Salt is 1 sodium, 1 chlorine. So solids had definite ratios, and metals are very different. Metallic bonding is such that you can mix in the solid state different elements to form solid solutions that are exactly like solutions in the liquid state, and there is diffusion. So no motion was considered. Solids could not move. The craftsman knew this. If you put gold foil on a lead statue, in 6 months it has diffused into the lead. And it was not until 1900 that somebody decided to test this, some academic, and he put the gold underneath the lead. Gold is heavier, so he didn't want gravity to push it down. And he found that it obeyed the laws of diffusion, the same laws that would be obeyed if you put ink in water and watched how it spreads. So, but it took another 20 years for the ceramics and the ionics people to realize that the motion in the solid state was caused by the vacant sites in the crystal structure. It's the vacancy that is moving, and it took another 30 years for metallurgists to realize this. So the time scale in the field of material science until I came was very, very slow. And this left many things to be done. So, oops, going the wrong way. Okay. All right, let me talk a little bit about myself and my life. As you already heard, I was born in Cologne, Germany, Jewish. My father was a lawyer. Very old family in Germany. We had been there, I guess some of my relatives had been there for 2,000 years, probably came with the Romans. In 1933, Hitler comes to power, and in March, my father was warned that he was going to be arrested, and we fled to Belgium. And we waited all summer in Belgium waiting for a restoration of law in Germany. It didn't happen. By November, it was too cold in the beach, and we moved to Amsterdam, where I had an excellent education in a Dalton school, which was an American-type school in Holland, but it was all in Dutch, so I didn't know anything. We traveled, spent half a year in Ortisei, Italy, but then returned to Holland. World War II begins on September 1st. On September 17th, my parents were lucky enough and smart enough to go to New York on the Holland-America line. And the day after we landed, I started school in New York. Now, I was a refugee, but as a small child, one isn't aware of the fact that my father was in danger. It was a very happy childhood, and it was very interesting, and I think it contributed a lot to my future career, that I lived in several countries for extended periods of time. I learned other cultures, and had excellent schooling. So in any case, one serendipitous thing about is that if Hitler had not come to power, I would today be a retired German wine merchant, because my grandfather was a wine merchant and I was the only male grandson, so I was sure to go into this business. Instead, I'm a scientist. And that's me at age 5 being a refugee. I don't look too unhappy, do I? Well, one of the consequences of having had this excellent education in Holland is that when I came to the States, I was bored out of my mind. Ordinary school was too repetitious. In the Dalton School, I'd been allowed to go at a faster rate. And so I wanted something more challenging than than what school provided. And I'd heard about a Brooklyn Technical High School. Now this, did this. And this was one where there was a stiff examination. They worked you very, very hard, but it was great fun, and I learned how interesting science could be in engineering, and I became committed to science. I went to University of Michigan to take a chemistry course. I continued to the University of California, where I met my wife. And at the University of California, there was another amazing thing. The examination to qualify you for the doctorate was not based on what you had learned in class. It was asking whether you had any originality. And so there were 3 proposals that every student had to prepare of research in some field other than his thesis. And I chose a rather strange topic, critical phenomena, which at that time was a total mess. People could not agree on what they were seeing. They didn't understand what was going on. It was a total mess. And there was a wonderful place to sort of say, well, this is what I would like to do. I'm going to solve this. But I didn't have to. This was an examination. I just had to state what I was going to do. And it turned out that I did a lot with this field later. After I graduated, while I was at the University of California, I became very interested in solid state. There was a new solid state physicist who had come to the university, and I took his undergraduate course, and I said, my gosh, there are such interesting things going on in the solid state. My professors were saying there's no chemistry in the solid state. There clearly is. So I decided to become a solid state chemist, and the best way to do this was to become a metallurgist. There was a new institute for the study of metals at the University of Chicago. I applied, and it was my first job, and I learned it was much harder than I had thought. Not knowing very much about metallurgy meant that I failed, but I managed, because of my 2 years at the University of Chicago, to get a job with General Electric, which was, at that time, the best place to do solid-state metallurgy, ceramics, and physics. After 10 years at General Electric, I became professor at MIT, But then in 1977, I had an opportunity to go work at a government laboratory. I came for 2 years and liked it so much that I stayed for 30. Now, at GE was a very unusual group, very small group, headed by David Turnbull, who is there. I'm here. John Hilliard is here. From this small group, 20 full professors came, and several chief executive officers of large corporations. This was an amazingly creative group, and I was very lucky to come into that because that's where I really learned how to do research and so on. Now, one of the things that they were working on was nucleation. And nucleation is the process in which a new piece of a material appears. It starts out small and grows, and it is like blowing up a balloon. There's a lot of resistance for a small particle to expand against the surface that surrounds it. And it's a very difficult process. It's like a birth process. In fact, the analog is, it's called nucleation, nucleus, a seed, and it's the way that my colleagues at GE thought everything new started. If you have if you have a water boiling, the bubbles start small and expand. If you have rain coming down, it starts from small drops that grow bigger. And it was considered to be the only method of doing it. Now, there was a much older method, which was called the spinodal. And it was an idea that had started in the 1870s that said, no, you don't start small. The thing is simply unstable. It just changes because it changes continue. And the amazing thing is that both of these ideas came from the same man in the same paper. But one of the things that occasionally happens in science is that one idea got forgotten and then rediscovered. And so by the 1950s, these two ideas were opposing ideas, and nucleation was winning. And people were abandoning this problem. So in Gibbs's thing, he considered the idea that there are necessary conditions for a substance to be stable. Necessary. If they fail, it's unstable. So there's nothing further to do. I mean, if I put this on here, it's unstable. It'll fall right down. I don't have to, there's no barrier. So he wrote down a set of conditions. And these conditions today are called spinodals. But if something is sitting here on this desk and I want it to fall down, I have to lift it up over a barrier. And that barrier is the creation of the surface. Once I've done enough work to lift it up to here, then it can fall the rest of the way. So nucleation in Gibbs's thing came when it was stable to all kinds of small changes, but big changes made it go on. And so Let me give you an example of a spinodal. This is van der Waals', this came in the 1870s. Here is a succession of graphs. Each line is how the pressure would go against the volume for a given temperature. So a normal gas sort of looks like that. High pressure, small volume, low pressure, large volume. But here's something funny. His equation of state had three solutions. So at this pressure, for this curve, it could be here, it could be there, it could be there. Well, he recognized that this was liquid. You have to really raise the pressure to make a small volume change. This was the gas, and if you change the pressure, it would go over. But here's something very funny. It had a negative slope. That is, here is one of these isotherms, and there are three solutions for this particular pressure. When the slope is normal like this, if I expand a piece of the gas, it has a lower pressure. So the surrounding material compresses it and it comes back here. If I expand it a little bit, it has if I compress it a little bit so it has less volume, the pressure goes up and it then pushes against the surrounding gas. Same thing is true here in the liquid. But here, if I increase the volume a little bit, the pressure goes up. So that little piece that has had the volume increased will push against the surroundings and keep expanding. Similarly, if I go down in volume, I go down in pressure, so now it's something that is more dense, but it can't resist the pressure from the surrounding. So this is an unstable region, and here at D and E are what van der Waals called spinodals. This is a place where the compressibility is zero. Volume doesn't change pressure doesn't change if I make small changes in volume. And here is something very strange. This is a critical point. Up to here you have liquid and gas, and the liquid and the gas come closer together, and here there is only one phase. It's totally stable, except here it has very low compressibility, so changes in volume don't raise the pressure very much. And then up here you just have a single fluid, no liquid, no anything. Anyway, let me show you. This is universal for all liquids. And here is I hope this works. Nope. Here is chlorine, which is an element. It's a yellow gas and a yellow liquid. And it's being heated. And here is the liquid. And the liquid is becoming, as it goes up, it becomes less and less dense, and the gas is becoming more dense. And the surface is now gone. There is no liquid and gas. It is only one fluid. And now what happens after they heated it for a while, they'll start cooling it. And when you hit the critical point, immediately below the critical point, the compressibility turns negative, and you'll see what happens. Did you see that happen? Now we have liquid and gas again, but it happened all over. Everywhere the I won't show it again. Here is the same. Now that was fast. And because things take forever, it takes days to reach for things to stabilize. Here are some experiments which my colleagues did at NBS. This is carbon dioxide, and these are 3 floats that are lighter than liquid carbon dioxide and heavier, denser than gaseous carbon dioxide. And here's the surface between liquid and gas. Here, it's above the critical temperature. There's only one fluid, and this one floats, this one is heavy, and this one sinks, it's light. Here is at the critical temperature. What's happening here is this is stable. There are enormous fluctuations. The stuff is so soft as far as compressibility is concerned that it gets denser and pressure doesn't rise enough for it to become less dense, or if it gets lighter, pressure less dense, pressure doesn't diminish fast enough. So this is stable, but these drops come up and disappear and come up and disappear, and they don't sink to the bottom because it's one phase. And here you have still opalescent. Now you begin to see a faint surface here. There is liquid here. There is gas here, but because you're so close to the critical point, things are still very cloudy. So here is this strange instability that is when one of the necessary conditions for stability, which in this case is that compressibility be positive, and that fails. And you can approach it at a critical point. You can come right close to where the compressibility goes to 0, and then immediately below things are totally unstable. So now let me talk a little bit about solid solutions. This is the crystal structure of lots of metals. It's called close-packed cubic, and these are and what happens is that metals really substitute for each other in such structures. You'll have it doesn't have to be all the same element, but there is a solubility limit. Just like in any solution, you can only dissolve a certain amount of sugar in water. After that, it doesn't dissolve anymore. There are solubility limits, and I'll show you a graph of the solubility limit for gold and nickel. This is gold, and at different temperatures, it can dissolve more and more. And finally, at 840, you can mix gold and nickel on the same crystal lattice in any proportion. And here's the solubility of gold into nickel, and it comes together. This is a critical point, just like the liquid gas critical point. And there is a spinodal right down here. It happens to be that the chemical potential, instead of pressure, has to increase, is required to increase with increasing concentration of an element. So instead of pressure, it's chemical potential. Instead of volume or density, it is concentration. But I've done a lot of work with fluids that mix oil and water. If I take my water to be methanol, methyl alcohol, and my oil to be cyclohexane, we'll have a curve like this and a wonderful spinodal at about 45 degrees. Well, here's one in metals. And So I expected that. And why did I do that? Well, when I first came to GE, it was a wonderful thing that happened to me. There was a contractor who had promised to finish a wing to the laboratory. And when I came to GE, he wasn't finished. And as a result of that, I had a desk in a blocked-off hallway with no window, and it was 9 months before my laboratory came. So I had 9 months in which to learn. And I learned everything that was going on. And one of the things that I learned that was going on is that a Swede had decided that he would draw a wiggly curve through here between lead on this side and tin on the other side, and decide where the spinodals were, and then he could quench down from here into the spinodal, and he would have a spinodal decomposition. The only trouble with that was that lead has this crystal structure and tin has this crystal structure. And there are totally different crystal structures, so I could conceive of having lead of this composition and tin of this composition. There's this crystal structure of this composition. They would still be different because even though they would have the same composition, they would be so. Anyway, Turnbull had defended nucleation theory, and he had gone into here and repeated the Swedes' experiment, and he showed that the way that tin precipitated was clearly by starting from nuclei and growing out. Well, I felt that that was not a fair test. So I argued with my boss, and that was kind of dangerous, that his work had not proven anything. So I decided to investigate gold-nickel, which has this spinodal. And I want to remind you that fluids that behave this way really have a spinodal right below the critical point. Well, what did I see? I saw nucleation and growth. Now, this is an embarrassingly bad micrograph, but the nuclei all started on these grain boundaries. They started from here and they grew out. This was nothing. This was just bad technique on my part. I never published this, but this was unprecipitated, and here it had precipitated. It was clearly nucleation and growth, and I was right where the spinodal should have been. So at that point, I gave up. I didn't know what was going on. I didn't understand why this was. Now, let me remind you that I knew about the critical points because of and the spinodal there, because of that exam that I had taken at Berkeley. So, anyway, 2 years after I arrived, John Hilliard came to GE, and we decided that we would investigate near the critical point nucleation. And the theory of surfaces that we were using was a funny theory which had been first proposed in 1805 and rediscovered many times since, and it was a fallacious theory. If I look at the density of two fluids on either side of a surface, I can take the difference in density, and that's a number. I can multiply it by itself, that's the square, and the surface tension, according to this 1805 theory, was supposed to be proportional to that. Well, if I make two surfaces, each with half the density difference, then that would have a quarter of the energy, so the two together would have half of the energy of the previous one, that would be less in energy than a single jump. So you argue that surfaces ought to spread out. But you have to do something about saying, well, if you have two phases that don't mix, the only way you can spread it out is to make some stuff that's in between, and that's really, that costs energy. So there has to be a compromise between those two things, and that was the basis of our theory. And then and that was a pretty good theory for surface tension near the critical point, that the one that's disappearing. And so we decided to do nucleation near the critical point. And all of a sudden, we found that there was no barrier to nucleation at the spinodal. So our theory was confirming our nucleation theory, was telling us that there was no barrier at the spinodal. So here something clearly was wrong. There should be no need to nucleate once you're inside the spinodal line. And yet, what about gold-nickel experiments? Well, gold and nickel atoms are 15% different in radius. So they are very different in size. And if you try to mix them on the same crystal lattice, there's a lot of strain. And this is something that was not part of the theory of the spinodal. And, well, by the way, this is Escher's version of our surface near the critical point. You have sky up there, and you have water down here. And if you spread the surface out, then you have things that are neither fish nor fowl in between. So there's a limit to how far you can spread the surface out. Anyway, so I had this problem of an experiment totally contradicting what I knew, and the only thing that was wrong that I could find out in the theory was that the theory was done for fluids and not for solids. So I had another serendipitous thing. I had applied for a Guggenheim Fellowship to go to Cambridge, England. I had planned to do all kinds of things, to be very, very busy. Turned out none of them could be done. And so I had lots of time for thinking. And again, you have to mix periods of thinking with periods of activity. And I found the answer. Now, this was, what exactly happens when you reach the spinodal? It turns out that the diffusion, which spreads things, now is turned backwards. Whereas in ordinary diffusion, if you have the material moves from where there's high concentration to low concentration. In this particular case, the thermodynamics dictates that material will move from low concentration up the gradient and concentrate on the high thing. So the cloud sort of collapses. But if the cloud collapses here, over here, there is another place where it's now collapsed, but here it hasn't, so it starts building up in this direction. And so the solution is sinusoidal, and it is the solution to a diffusion equation. but it is a different diffusion equation. What I didn't know at the time, that mathematicians had done a lot of work with the equations of diffusion, and they had found that it was ill-posed, it had no solutions. You could not tell after the ink has spread through the water where it had come from. You can't run it backwards. And running diffusion backwards forward in time is exactly the same as running normal diffusion back in time to try to predict what happened before. I had added a term to this diffusion equation which regularized it, which meant that the mathematicians suddenly had a toy with which to play. And so the Cahn-Hilliard equation is a diffusion equation which solves a lot of problems which occur everywhere where things move together, whether it is a population that's moving together or economics where the money is moving together, and so on. So, and the other thing that came out of it was that the elastic behavior was explainable in this equation. This was an equation which said if you have diffusion in a solid, you distort the solid. And that energy modifies the diffusion, and elastic behavior is directional. In a crystal, there are soft directions and hard directions, and here is spinodal decomposition in a glass, which is the same in all directions. And so you have, this is now made visible by impregnating liquid lead into a glass that had undergone spinodal decomposition. Here's a magnetic alloy, alnico, and you can see that within this crystal, the precipitates have lined up beautifully. I want to show one quick simulation, or maybe I'll leave that for here. This is the other important equation that came out of my research. Here's another kind of critical phenomenon. This is from the thesis of Sam Allen. This is now all inside of a single crystal, seen in the electron microscope. Here we are 4 degrees from the critical point. Here we are 60 degrees from the critical point. You can see the critical opalescence. Now here the surfaces are, gravity doesn't play any important part here, so they're not flattened out the way they would be. And the combination of the equation that deals with this and the equation of spinodal decomposition. Here is something I put in for Arthur Hoyer. Here he did the moon through the microscope, and here you see the same thing in rocks that he got from the moon. It's a wonderful little book. And here's spinodal decomposition on rocks in the moon, and here is the other kind. Here are dendrites, and the only important thing about this is that the combination of the two equations for these two different processes are used to solve the dendrite problem. And here is an example of a computer calculation for a dendrite. You see here the darker brown is that the alloy element concentrates here and in the center, and the green is the temperature and the liquid around the growing dendrite. So let me all right, where does backward diffusion occur? I want to close with this, the domino effect of paradigm building. I hope you've noticed that I went and looked at nucleation and at surfaces near the critical point and found things about the spinodal. Almost everything I've done has been serendipitous in the sense that I was prepared with problems, and then I would work on something in another direction, and it came out. And so these are all the serendipities that I've wanted to talk about. And I thank you all for listening. And that is, my time is up.
ありがとうございました。どうぞそちらに。それではご講演いただいたカーン博士に花束の贈呈がございます。カーン博士にもう一度盛大な拍手をお願い申し上げます。